Hi there, I'm John Lindstedt, and thank you for attending virtually the Cognitive Speed Bump, or How World Champion Tetris Players Trade Milliseconds for Seconds. By way of introduction, I am a new assistant professor of cognitive science at SUNY Oswego in the computer science department, and this work is part of a project I did with Wayne Gray during my dissertation at Rensselaer Polytechnic Institute. So, this is a project about extreme expertise. The goal being, if we can better understand how expertise manifests in real-time complex tasks, particularly in the strategies that are employed by experts, we can then better understand how to train experts, right? We can come up with better routines, figure out, what is holding back a novice, right? And the thing about a lot of expertise research is that in a typical study on expertise, you're looking at tasks that are not especially time pressured. So chess, you have all the time in the world to deliberate over what you want to do at any given moment. Not all the time. Tournaments have clocks, right? But not quite the same as a fighter jet, where you are in the cockpit making life and death decisions continuously, trying to optimize your own life. So how do we kind of bridge that gap? We like video games, in particular Tetris. So Tetris isn't quite a cockpit, but it has a lot of nice features. It's this puzzle-solving game, really well-known around the world, so it's easy to find good players. But it's this manageably complex task. We are able to analyze and both capture all the data pretty easily and analyze it in the same form. It has inherently increasing time pressure, so that's good. It pushes the players along that continuum of time pressure that we want. And there's multiple viable strategies, there's multiple decisions to make at any given moment, and it has this built-in scoring feature, which is quite nice. The players know when they're getting better, and we can use that to assess their skill. The current study attempts to compare novice, intermediate, and expert strategies in Tetris, specifically this Zoid rotation subtask, how you rotate that block. We also are looking at the cognitive temporal costs of these strategies, and using this quasi-experimental design, we're finding players of different skill levels in the world. We're not creating them ourselves. Great feature of having a well-known game. A little bit of anatomy of the game. On the left is a itty-bitty game screen. That is, the Zoid is the block you are controlling. The pile is the pile of other Zoids you've dropped that are growing, and could, if it reaches the top, you lose the game, but otherwise you are clearing those lines to score points. You have 5 controls available to you as a player. You can move the block left and right, the Zoid. You can drop it, and you can also rotate it one of 2 directions. That will become key. To give you a sense of the time pressure in the game, there's at level 1, it's 1.25 rows per second is how fast this thing is falling. Whereas by level 16, the block is falling 20 rows per second. You have less than a second to decide where to put this thing, and more or less how to get it there as well. You could see how that might cause a lot of very small things, like, say, rotation strategies, to become very important if you have to waste time rotating a block improperly. So let's talk a little bit about the Zoid rotation behaviors. There's 3 categories. Static Zoids don't rotate at all, so we can just kind of consider them a baseline. Flipping Zoids, on the other hand, have 2 different orientations. So it doesn't matter what button you select to rotate them. But rotating Zoids have 4 unique orientations, and they rotate sequentially through them. So let's look at how this might play out with the different buttons available. So here's a T-block. Let's say we want to get it from orientation 0 to orientation 3. The goal is to move through them in sequence. If we assume a clockwise default rotation button, monorotational strategy would involve just rotating the default direction 3 times. Easy peasy, not much thought involved. You could get very fast at this. Boop, 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 and you have finished, right? But there's another option available to you, and that's to employ a birotational strategy, where you take a moment to decide the rotational direction, and I say moment, a cognitive beat. Then you end up rotating only once in the non-default rotation direction, and then you're done. These can be critical. The monorotational strategy has very high motor costs. Sometimes you are hitting a key press 3 times when you have less than a second to maneuver this block. But it has very low cognitive costs. It would be easy to adopt and easy to train. The birotational strategy, on the other hand, has much lower motor costs, on occasion at least, but a high cognitive cost, making it more difficult to create in the first place, right? So, how do we approach this? I created the software MetaT in Python. It is a research platform version of the NES Tetris, the one that people use all over the world. It's also the most unforgiving version of the game. Sorry. So it gives us very high fidelity data. We can play back at millisecond level, down to the wire. We had tournament players. All this data is collected in the wild at actual tournaments. Some that we hosted ourselves locally, and some that we went to in Portland. So they all played at least one game with the same exact Zoid order, just to at least control for the opportunities available during a game. And we looked at the strategies used during and the performance during the highest successful levels of performance before they fail out, right? The populations we sampled, we had 10 novices. These were low-scoring, free tournament entrants who just kind of washed out immediately. We wanted to look at them, right, just to see how they behave. We had 10 regional champions who won our local tournaments, and then we had 10 global champions, world champion Tetris players who had thousands of hours of practice, who go to this tournament every year. So we had 3 basic research questions. First is a sort of sanity check. Do these skill categories actually differ significantly in their performance, in their game scores, right? Second is who actually adopts which strategies. And then third, do extreme experts, can they shave off any cognitive costs associated with the most efficient strategy? Or are they sort of saddled with it? So, skill and score, sanity check. This is pretty straightforward. The global champion players, all categories differed significantly. Now, we did use a 6th root transformation just to make the data most normalized. But no matter what the transformation was, these categories all differed. This was sort of just convenience sake, not really a theoretically loaded question. So yeah, they certainly differed in performance. That's good. At least as a baseline, we can understand that they are different categories. Next question is, how often are players using a non-dominant rotation button? On the left, we see novices almost never. Regional champions start to flirt with the idea, but global champions make extensive use of non-dominant rotation. So they are using both buttons, whereas most other players are kind of sticking to one button. And on top of that, the question remains, like, does it actually help? And we quantified that to see how many unnecessary rotations to get into the correct orientation were used for each Zoid. And the global players, you see, almost never had an incidence of an unnecessary rotation. Now, finally, the findings about using these different strategies. We see that regional players almost never use birotations, but global players use them almost universally. So, looking at their reaction times now, we can break apart and say what is happening for each of these different strategies with fairly skilled players. So the regional champions, using the monorotation strategy, saw no difference at all in reaction times for each Zoid type. They are evidently not, there's no cost associated with whatever their strategy is. They are just going and going, right? Makes kind of sense with the monorotation strategy. The global players, however, using the birotational strategy almost exclusively, we see significant differences in their reaction times. It takes them longer to decide what to do with rotating Zoids. Strangely, it also takes them longer to decide what to do with flipping Zoids. Quite interesting. So, summary of the findings. Player skill categories are predicted, or they do predict game performance, kind of an of-course moment. Regional champions strongly prefer monorotation, global champions strongly prefer birotation, and strongly is sort of conservative. They almost universally use these. And it helps them avoid unnecessary key presses. But even the extreme expertise of these global champion players doesn't mitigate this cognitive speed bump of deciding rotation direction. So, what we think is that this super consistent pattern of this irreducible initial reaction time for the birotation strategy suggests a different memory structure involved, a more complex memory structure to navigate. Even Zoids for which there's no difference what direction you would rotate, they see a bump. So the idea is players are likely navigating some different structure to achieve the rotations. Since monorotators don't see that increase, they're a little slower overall, but that's maybe just a skill function. So this suggests more complex memory structures. The implications for skill acquisition are that cognitively overwhelmed novice players are unlikely to adopt the more complex two-button memory structure. Because they're spending all their bandwidth elsewhere. They're trying to learn the task. And the simple strategy satisfies, right? There's no real time pressure. They're not at the level where that 150 to 250 millisecond savings is going to save them anything. So, but conversely, it may be that learning to use both rotation buttons early would prevent becoming entrenched in this single button memory structure. Because even some Classic Tetris World Champion first-timers actually struggle with this. They have to relearn the rotation behavior. So, limitations of this. This is a quasi-experimental design, right? And it's a very complex task with complex data. And so there's lots of room for additional interpretations. What role, for example, might planning play during the previous episode, the previous Zoid? We have not looked at that yet. So drilling down on this, we might look at a tighter experimentation, like a simplified Tetris rotation task that we can do in lab or at least on site, a little more controlled about looking at these rotation strategies, maybe using some eye tracking, right? And also modeling different memory structures to see what might be plausible that would cause these different bumps in reaction time to accessing the memory structures, right? So, but on top of that, this is also just a good first step to a bright future of this kind of work where we can examine these same kinds of strategies across many complex tasks, anything that is sort of, manageably complex. So, conclusion, this has been an attempt to catch lightning in a bottle, I like to call it, with these high-fidelity behavioral data traces from really skilled players, but also from novices. We're trying to chart in high-res the behaviors in this complex task with players from all over the spectrum. We also did some sort of routine verification that, expert players are much better at the game. They employ different strategies, and those strategies offer them additional efficiencies, right? But we also uncovered this very consistent speed bump in their reaction times, and it's even more consistent. I can share some other figures during the questions section, potentially. For now, I'm attributing that to likely differences in the memory structures involved, and the support for more complex strategies would require these more complex memory structures. And, this is beginning steps toward assessing other manageably complex tasks. Thank you. I regret that we couldn't do this in person with your lovely faces, but I'll look forward to the questions. Take care.